Basically, the IBM folks, including myself, were pushing for algorithms part. It's a long story. And Anna Karamanska from NYU and her students, they helped us out with theory. So it was kind of really like a combination of joining forces. And also Ravi, who is now at MIT, was our student at that time and was helping with running experiments. But basically, it all started with questions you keep asking yourself. What would have happened if history was different? So you probably read Jorge Luis Borges, maybe not, but there is a story, one of his famous stories, called Garden of Forking Paths. Have you read it? In any case, the idea is like he's talking about some strange book written by some Chinese emperor where it's like total mess, there is no logic in that seemingly. Bottom line, the emperor was trying to write a book where all possible trajectories, the whole tree in the history, would be reflected. That's why characters that are dead in the first chapter are alive in the third. And anyway, so if you think about it this way and ask yourself, so what would happen if you backtrack in the decision tree of AI field and make different choices at critical points? What would have happened? I mean, essentially, it's what's going on right now, because you can say, well, we can go all the way back to the model of neuron, McAuliffe and Pitts, and say that let's redefine that and let's make it more sophisticated in various ways, more biologically plausible. Blake just talked about one way to look at that. Capsules are indeed relevant here. That's why I mentioned them. Various ways of looking into neuronal unit and modeling it in some way in more details and better. Whatever better means, that's a separate conversation. But yeah, we could have made different design choices at that level. Next question as well, learning algorithms. We all know that backpropagation for now is, well, pretty much standard, and most of software implements it. And for good reasons, it does seem to work well. But still, the question is, well, there are many other optimization methods that could have been used, right? So what if we tried something else? And people tried, including us, and I'll talk about that story. And the gist of it is, I think it's important sometimes to look at the garden of forking paths, try to go back and see what if in the decision tree you would choose a different branch. Just saying. Well, this is more like you all probably have seen it multiple times before when the interview was, well, Jeff was giving this interview about issues with backpropagation, though it was, I think, in the context of supervised versus unsupervised learning. But essentially, he was totally trashing backpropagation, saying that we need to throw it all away and start again.
News.
Well, that's not fake news. I can send you the link. But in any case,
I actually know because I spoke to Jeff.
Yeah, I mean, Jeff likes to say things like, yeah, I need to throw it away and start. And he was saying that I'm pretty sure that the next advance in neural nets going to be probably done by some student who is sitting in the audience, is deeply suspicious about everything I'm saying. And he's right. So please be deeply suspicious about everything we're saying.
Sorry, but just to be clear, I mean, what Jeff was talking about in that interview, which he didn't actually know he was being was one first.
That's not fair.
And the second thing was that he was ultimately arguing for unsupervised learning.
That's what I said. It was a context of supervised versus unsupervised, saying that if you treat everything as supervised, then you use backpropagation. But what if it's unsupervised? Then what do you do?
I mean, today's best algorithms, supervised, unsupervised, and reinforcement learning all use backpropagation.
Yeah,
that's right.
Actually, unsupervised autoencoders. By the way, here is a good thing, and Gael will talk more about that. But here is a little bit of alternating minimization mafia. So there is not the only way to train even autoencoders. And actually, let me just continue, and then I say where it's coming from. Well, with backpropagation, I mean, of course, there is always wrong. Something is wrong with everything. I mean, nothing is perfect. So it's pretty good, but, well, people complain about if you're motivated by biological plausibility, if that's a question, of course it doesn't fit the bill. And the list of shortcomings is long, and I don't want to go into that. Blake already covered quite a few. And even just looking at the last year NIPS paper, well, new RIPS, I just cannot switch to calling the good old NIPS by this strange new name, but never mind. So there was a paper by Sergei Bartunov and Timothy Lillicrap and Jeff Hinton and a few co-authors where they were trying to assess scalability of several more biologically plausible algorithms, including different flavors of target propagation. I'll talk about that a bit more. And the arguments why they are not biologically plausible, among many other things, is, well, first of all, if you think about the algorithm itself, it only works on weights. So it doesn't explicitly model any neuronal activity, and it kind of assumes that neuronal activity is deterministic function of the input, which is not the case. I mean, it's extremely simplified version. So even if you have an algorithm where the neuronal activity is at least noisy and somehow explicitly updated, that probably would be a bit better. Again, it's just like tiny bit. I don't want to even call it biologically inspired. It's like tiny bit inspired. The weight transport problem, yes, that's a separate problem. We're not going to address it in our algorithm, but target prop and feedback alignment, they address it. That's the problem that you have same weights when you go up and down the neural net, and that's not exactly the case in real neural networks. But again, Blake is a better person to discuss those details. There are many other issues, like you need precise clocking between feed-forward and backprop phases. It's not exactly what's going on in real brains, violation of Dale's law, and so on and so forth. Even if you don't care about neuroscience and you just want efficient learning algorithm, there are still some issues. Although people could argue that there are many approaches to overcome those issues, and that's true. Vanishing gradients, I know. So that's always a debate, is it still a problem or not? But even though it might be very much alleviated by LSTMs and other approaches, as long as you have chain of gradients, and this chain can be long, and your matrices can be ill-conditioned, it's always a Pandora box. You may have exploding or vanishing gradients if you have that long chain. And that does happen apparently, especially in reinforcement learning, especially in non-stationary reinforcement learning. That's kind of the case where the vanishing gradients seem to bother people a lot. I don't have personal experience, but that's what I keep hearing. So it would be nice to get rid of that kind of once and for all, if possible. The good old question about what do you do if you have binary functions, if you have any kind of non-differentiable nonlinearities, and computing gradients is just not convenient. You have to do something. Like with binary, you have to do straight-through estimators, essentially ignoring those bad non-differentiable functions, or some other tricks. If you had some way of just dealing with those things locally without having to take chain of gradients, again, maybe it would be more convenient. And last but not least, it would be nice to have some parallelism in weight updates. Again, people may say, well, there are various algorithms that essentially gonna process mini batches in parallel between layers, like one layer processing one mini batch, the other is processing the other one. But it's still not the parallelism at the level of the same mini batch. Anyway, people tried different approaches, starting from actually Jan's thesis, where he mentioned backpropagation, but he also mentioned that we could have just formulated constrained version of the optimization problem for neural net learning. And then we can rewrite it as Lagrangian. And then, in principle, we can solve it with various methods. Later on, he tried to develop the target propagation algorithm, which didn't immediately work that well in terms of performance. And then, well, yeah, Yoshio had a paper with students on different target propagation with somewhat improved results. And then the whole kind of chain of papers, including that paper that I just mentioned by Sergei Bartunov and this one at the last New Reefs, where they made yet another twist on the different target propagation. So the bottom line with target propagations was that they were introducing activations, hidden units, as explicit variables. And they were trying to essentially not only optimize weights, but optimize values of activations to fit the proper target, what they should have been. So there are many more methods that have this common property of introducing auxiliary variables. The list goes on, but I mean, one of the papers that kind of, I think, started this line of research recently was 2014 paper at IIStats, the method of auxiliary coordinates by Carrier-Perpignan and work. So essentially, they just took the same formulation as I think Jan LeCun had in his thesis, Lagrangian form, and actually not even Lagrangian, they replaced the weights. I'll show the equation later. Replace the weights by the same kind of common weight, so it essentially try to optimize that. There are many other methods after that, and perhaps not everything listed now, because since we had this paper out, those methods just multiply like rabbits on arXiv. So when we submitted to ICML, we immediately found the other day another paper in ICML format talking about yet another auxiliary variable method. But it was okay. The problem is that most of those methods, they seem to be offline, so they batch. So they are not really scaling to really large data sets, and they are not really scaling to any continual learning if you want to do continual learning, at least as far as I know at that point. And with target propagation methods, they are different. They are also introducing auxiliary variable methods, but they have now two sets of weights. Unfortunately, it's not clear how to write one objective function that drives target prop. Target prop is formulated in terms of local updates. I mean, it's probably possible to write it, but it's not that immediate. And unfortunately, as Ethan's paper showed, it didn't perform that well as compared with backpropagation on certain standard benchmarks. So people kept trying, including us. And my manager kept asking me, like, why did I waste my own time and time of so many people for more than a year on something that just doesn't work? So next time I decided not to mention this project at all, and we kept working. So finally, thanks to many students and months of experiments, things started taking some shape. And here is roughly the idea. Again, at that high level, the idea is quite common to several approaches. What will be unique, actually, is that our auxiliary variable approach is online. That seemed to be the first online. And, well, thanks to Anna Karamanska, we have some theory, apparently, again, first time, showing that the online stochastic alternating minimization actually will converge. I guess, I mean, it's not that terribly striking results, but it was nice to know. So you introduce explicit variables that stand for your activations, and essentially you separate linear part and non-linear part. The part will be called codes, so that's kind of, you just take the linear transformation of the previous layer, you get your code variables. Then you apply nonlinearity with noise, and you get the actually vice versa. Noise is applied. Essentially, those codes are, you can say that they are Gaussian variables in a Bayesian network. You view that feed-forward neural net essentially is Bayes net, which is pretty much the case. It's just in regular neural nets. It's a Bayes net with deterministic conditional probabilities, pretty much, except for the last layer. And once you have now those noisy activation variables, the codes, you can alternatingly minimize your weights and those variables. Idea is like as old as, I don't know, any kind of alternating minimization algorithms. Which the first thing that comes to your mind, if you come from the probabilistic graphical model background, like myself, what do you see when you see hidden variables? Well, you run EM. If you come from compressed sensing, dictionary learning background, and Gail will talk about that, and that actually did come from there, or from matrix vectorization. It's very similar. You have hidden variables, and you run alternating minimization. For several years, I was going to several machine learning conferences and asking people, so why nobody is doing alternating minimization? The answer ranged anywhere from because we don't do it with neural nets. That's it. Because it doesn't work, we tried.
It's not written in the book.
Because it's not written in the book. And finally I asked Jan. Jan said, I tried, doesn't work, don't waste your time. And Marco Lorenzato tried to do it with RNNs, and it didn't work that well. And he said, why didn't Jan told me not to waste time on that? I said, well, the problem is he told me, and it didn't change anything, see? So,
I tried things like this.
I know really well what you mean. And my manager had a good point when he was worried. Because you can easily waste a lot of time on this. But it's actually interesting because, I mean, there are some pluses if you achieve decent performance. You get algorithm with different properties. And I think it's always healthy to have a toolbox with a set of tools rather than one hammer that you're going to use for all size nails. So this is another tool potentially, or this kind of class of methods that might be sometimes helpful. Again, still at the high level, what we're looking at is a formulation that the method of auxiliary coordinates looked at as well, and pretty much Jan sees this same thing. Start with the objective of your feed-forward neural net training. You have your loss function, you have your output y, you have basically the function of the last layer and weights there, and then you write it down as a compound function, as usual. Just like in Jan's thesis, you can rewrite it, introduce it, constraint formulation. You just explicitly put the activation variables, and you say what they're supposed to be equal to. And the critical part, we're going to be using the pre-activations, the linear codes. It's just more convenient. I'll show why. There are multiple methods. Some use non-linear, some use linear, some use both constraints, and you've got your Lagrangian objective, and you actually cheat a little bit. Instead of doing true Lagrangian, you replace all the coefficients with So this is exactly a Carrier-Perpignan type of formulation and simplified the other. The question is now, okay, we can do
value function formulation.
Yeah, whatever you call it. Yeah. The only problem is that it didn't look like in the literature people tried to provide the online algorithm for that. So it was batch using in alternating minimization the whole matrices. So, yep.
Sorry, I just want to make sure I understand. So you ultimately got two different loss functions, one of which is just your
one
loss,
is just a constraint,
and the other is just making sure that you're meeting.
Yeah. So basically,
and your constraints are basically try to be linear.
Try to be close to what you should be. So
what you should be is linear, right?
Yes, because it is in neural net. It is linear. It's before you apply nonlinearity. So this tells you this should be close to what it actually should be if you have your neural net defined regularly. But I will relax it and I let it be a little bit off.
Right.
Not too much though. Yeah.
Yes.
And the nonlinearity is rolled into the next layer.
Yes.
It's just for reasons I explain a bit later. I mean, there are several ways to do that, and you don't have to do it this way, basically. Okay, it's all simple. And then you just do very simple thing. Oh, did you have a question? What was it? Yeah, capital C?
Small c or the small c is the same thing.
It's like, okay, so basically this is a matrix. If you collect all the, okay, imagine you have the input vectors x. You can say you have a matrix capital X where all the input x's are collected. Same thing for c's. Yeah, I mean, so it's essentially W here means all the weights, and capital C means all the codes at all layers, like whole matrix. Oh my gosh.
Why is it minimizing over C?
What?
No, because it's free. You're allowing that. different from the default pattern.
Yeah, because in a standard neural net, it's not a variable.
It's not equal.
Yeah, it doesn't have to be equal.
Like you,
It can. It's a simply linear Gaussian variable, and now you just got your base net. You can call it neural net if you want. Whatever you call it.
That's only valid if you
ReLU was here. Yeah, ReLU was used here, but in principle, you can use whatever. You just will implement each layer
So
of
here's another way to
optimization.
think about it. You have the 3 port values. Allow a slightly different value to lower loss. Difference between the two is the thing we're looking at in target propagation.
Well, you could, yeah.
What is subject to the pressure of the law, and so you're allowed to change the from the
Right.
forward value.
Right, essentially, yeah. So just, you can say I added noise to those activations so they actually became variables to optimize, because before they're not variables, they always have, given the input, they have deterministically same, well, they're deterministic functions of the input. Now they're not deterministic functions anymore, they're stochastic functions or random variables. That's all. Again, nothing new here yet with this formulation, but then online is something new. And yeah, so offline, for obvious reasons, will not scale to either large data sets or what we were interested in, continual learning. Although we didn't test it here in this paper on continual learning and non-stationary tasks.
But step 4 should now be like
Okay, so here is a good question indeed, because I mean, this is just one way to do that, and perhaps not the best way. Lots of room for improvement. That's what I'm saying. I mean, there are so many design choices in the algorithm because you can do it once. So basically, what's going on? You got your input or mini batch, whatever. For simplicity, say just one sample. You encode it the usual way, as you would, assuming just the deterministic. From the output, compute loss. Now, what you do, you need to still propagate that error somehow. Take that loss and you start updating those codes, like in target propagation, but the difference is you do separate. And then once you update them, you fix them, and once C's will be fixed, that will decouple the whole chain into multiple parallel updates at each layer for weights. So weights will be just updated in parallel, and that update is, by the way, very easy because it will be like a quadratic function.
actually closely related to equilibrium.
Yeah, okay.
because basically
Yeah.
you're taking the push towards the correct answer at the top, propagating it back through
Yeah.
the network, and then training the network to be more like that in the control.
Yes. So this is more specifically, I thought people may want to see code more
You should
specifically.
say mathematically what step 4
Here. Okay. So here we are.
You really just backpropagate with the metric.
You keep the symmetric weights. Yeah. So that problem is, I mean, it's
Right.
not feedback alignment. It's not target probe. The only little bit more biologically plausible part is that activations are now explicitly handled and they are noisy. And updates are parallel. But again, that's why I say it's like quote unquote. It's in the same kind of category as target probe, but even a little bit less plausible. But the point was, okay, plausible or not? Like how we optimize it differently. The encode input is trivial, as I said, it's just like update codes. You pretty much at each layer, starting from solve the optimization subproblem for the codes in the paper, or I can write it down. But that's where nonlinearity matters, and that's where you have to implement whatever you want, ReLU or anything. Yeah, so it was all in PyTorch. And in principle, I think we didn't do it, but you can go deeper into PyTorch and change the updates there. But it's a separate conversation we can have offline. Anyway, so you solve sequentially. So this part is still sequential. And here is kind of think about parallelization. When the other algorithms, the previous ones, Carrier Perpignan, they used that formulation in batch setting, they were completely parallel, code-wise and weight-wise. But if you online, it seems like you will have to sequentially propagate each sample or each mini batch. So the only parallelization that remains is at the weight level, but at least better than nothing. So you solve all your optimization for codes, and now you essentially do your weight updates. Ugly. And by the way, there are two ways to do that. Say now you have all the codes fixed. Have all the code fixed, each layer subproblem for weight updates is totally independent of other layers. And okay, there are at least two ways to do that. You can simply perform SGD step, but locally on those weights, independently, not computing any chain. Or you can use a trick that Julien Moral used in his online dictionary learning, where all this stuff is coming from, actually. Old paper from whatever. You remember better. 10,
was 2009.
9, yeah. There was an interesting trick there, which gives you basically two covariance matrices, which can serve as a memory. And it remains to be seen if that memory can actually really help learning, but that's what I'm curious to figure out. So either you do simple SGD, and actually empirically so far it works better, or you do the following thing. That's what you need to solve at each layer separately. Okay? This is fixed, those kind of from top and bottom of that layer. And solving for weights is just a simple sub-square, right? But it's online problem. You don't want to keep the whole thing in memory. You don't want to keep a bunch of samples, the whole history, the whole point of online, right? So what you can do, again, not us, it's Julien Moral. You can rewrite it, or actually it's even before that, it's no thing. You can rewrite this function in this form of these two traces, where you have two matrices that effectively accumulate the outer products of codes between layers, and the matrix outer product. Yeah. So so one is across layers, and another is within. So essentially, it's a co-activation matrix. One is co-activation within layer, and another co-activation between them. Because essentially, this problem is exactly online dictionary learning, where W weights are beautiful. That's it. It's just like piggybacked on that. And the reason we got to that because we were initially just doing the online dictionary learning and changing architecture. And we wanted to have something like that, change architecture in the whole deep net. Anyway, so there's those two ways to optimize it. And how much time do I have? Lesson? Okay. Okay, so you do that. You ask Anna to prove theoretical results, and she does. So anyway, I'm not going to go into that. And like, if you'd like, we could go over the paper. But bottom line, what it says that this alternating minimization, or even weaker version of that, because the result is proven, to be honest, for a much weaker version of the algorithm, which assumes that every time you see a sample or mini batch, you only do one SGD step in one layer and you move on. And for that, even kind of less, slower optimization, yeah, if you start not too far from local minimum, you'll get there. It's basically just a sanity check.
Do you have a result of the quality of the game that you have to convert or not?
Look, it's nothing like what Myral had in that paper. I wish we had that.
The paper is
not
technically wrong, I'll mention.
Okay, but it was good because what he was showing was different type of result. Not that, okay, it will converge, fine. What he was showing that if you have stationary distribution and you do your online approximation of the true objective that you would have had if you got all the data, you'll get a dictionary or the weights, not the same ones, but same quality in terms of objective function. We don't have that result. Actually, it's probably possible to show. Why not? It's just, I don't know how to do it with more than one layer. Anyway, I'm diverging as usual. Results. Okay, so we didn't do ImageNet. What we did essentially was to see if this kind of makes sense. It doesn't have to beat everything, but at least is it making sense? Is it competitive on standard things? MNIST, CFAR, fashion MNIST, stuff like that, some simple RNNs. And yeah, pretty much it kind of matches performance of SGD, Adam, and such. It's interesting that it's also often learns a bit faster. So you can possibly even use it as a good initialization. Kind of on smaller data, it learns. So let's see what's going on. On a MNIST, right? Again, architectures were simplistic, just like everything. Like you have a few layers, you try 100 nodes, 500 nodes, this and that. Same with CFAR. One point was to show what happens to all these offline methods. There was kind of state-of-art offline alteration minimization by Taylor from MySimal 2016. And with offline, yeah, they're way behind. So that says who cares, because everybody would compare with SGD and Adam anyway. But just saying that it's like by far better than doing it offline. And in terms of SGD and Adam, they were kind of comparable. And same thing with CFAR. So the red thing was our method, like AM. And Adam were black and blue. So it was kind of even sometimes slightly more accurate or slightly less accurate, or pretty much the same. Then if you zoom in, that's what I was talking about. It often learned a bit faster than SGD and Adam, kind of consistently faster. On RNNs also, so we often saw this first faster learning, and then they both kind of get it. I don't know why is that. I cannot guarantee faster learning or faster convergence at the beginning, but that's just empirical observation. I mean, so it's kind of sometimes better or similar. And then we just, again, we played with relatively toy things. It's comparable. Again, it learns faster, and then it's pretty much the same as the Adam, and they both better than the sequential at least with simple RNN. So kind of here and there, and there was a huge data set, by the way, Higgs data set from Taylor's paper. Taylor's algorithm was offline and parallelized, but data parallelized, not layer, not weight parallelized. Otherwise, how would they manage that? That was a clear win, because basically ADMM of Taylor, it was getting to this benchmark, and we were getting there with 0.01% of the data doing it on one method. Then outperforming. So okay, so basically offline auxiliary variable methods definitely were out of picture very quickly. And yeah, one more thing we tried. Yosha's paper from ECML, you had this basically a binary network. Toy binary network, but just was interesting to see like what it's going to do on those non-differentiable non-linearities. That's pretty much as well performance-wise as what you guys get, but again, it does it faster. It just essentially gets same accuracy, but less than 20 FOVs. Your picture showed about 200 FOVs to get there. So it's kind of behaves comparably, somewhat better, sometimes worse and so. So bottom line, it's kind of it's algorithm that performs reasonably well, at least on those things we tried so far. Yes, you have some theory, which is good to have just for sanity check, but it doesn't help you improve performance as most of theory. But the interesting thing is the algorithm has very different properties. So it, by definition, does not have the chain of gradients. So you can imagine trying it in RNNs maybe, or reinforcement learning and so on. Although I suspect if the problem is inherently hard and there is a reason for vanishing gradients, then probably any other algorithm will have some other problem. Maybe the alternating minimization will. There are probably no free lunch. If the problem is inherently hard.
Weekly second order by capturing the
Yeah.
covariance of your weights. So you've got the A or the B matrix, I don't remember
Yeah.
which one. That one captures the covariance of the brain, and you're probably weekly second order. Probably much, much more robust definition.
Perhaps.
My
But
intuition.
that remains to be checked. So the good things are, yeah, weight updates are parallel and independent. So if you need speed up there, you can do it. If you have something extremely deep, maybe it will be helpful. No change, that's fine. If you need your non-differentiable nonlinearities, it's easier to code at each layer, just a separate optimization for that, than having to think how to maintain a chain or just ignore nonlinearities altogether like people do with straight-through estimator. So it has those complementary properties. It does have its minuses because honestly, after that, we kept trying and we tried on like serious size ResNets and it didn't work well. And then basically what it was doing, it finds on training data equally good solutions or better solutions. So it optimizes as well as, and then it doesn't generalize. Yeah, welcome to the good question about flat minima, deep minima, whatever it is, but why on earth it finds better solution and essentially overfits. We tried regularization with sparsity. We actually started with that. Didn't really help. So bottom line, and by the way, it's kind of seem to be very kind of sensitive. You don't regularize or you over-regularize. And some trade-off in between seem to be hard to find. It might be different regularization that you need, not sparsity. Well, it's a good question. So there are several good questions. So there is lots of work to do with that because it's far from kind of really, well, I mean, you can add it to your toolbox right now, but it would be probably better to improve it. There are many ways to improve it. And as you mentioned right now, the whole idea of just doing one iteration of code updates followed by one iteration of weights. We tried to do it multiple times, but it was never really systematically tuned. So there are all these decision choices in alternating minimization schedule that can matter a lot. And that remains to be explored pretty much. I think I'm done pretty much.
So, okay, I think I think that it's a very interesting algorithm, and I appreciate the points. But in terms of the biological interpretations, like, I guess one of the things I wonder is, so you're saying it's online, but like, it's not actually properly online, right? Because you have to do a forward pass through the network, and your backward pass to just calculate.
It's worse than the back.
And then you have, that's right, it's actually worse than the back.
It's a solve on each layer pass.
That's right.
No, I mean, it's just as just like SGD, like you feed it one sample and it processes it, it encodes it, right? And then it optimizes it. So in that sense, it's online. I mean, it doesn't require any.
Well, I mean, we can discuss Yoshua's extra point, but here, I think you will agree to this. It is as online as SGD.
Yeah, it's as online as SGD.
Right.
And that was not something that alternating minimization methods could do. Yeah, they didn't do that. Yeah, so now it is as online as SGD and as online as target prop. So now it's at least as online as those guys.
Right. And so then I guess my question is, though, like, what do you actually see as, so as I said, I think it's an interesting algorithm, and I think the theoretical convergence guarantees and everything are really cool.
It's nice to have, but yeah. It's not about brain. It's about.
Okay. Fair enough.
As I said, like I'm very pragmatic. When I say neuroinspired, if it helps, it helps.
Let me argue why something. Brain is big. computation to it. Local computation is done. I mean, so people have been what's house primitive processing has all kinds of ideas. Not completely free.
Man, it's between.
You would get a second order effect.
Yeah.
So I think the benefits,
So
and I'll
that's-
talk about this, the benefits are what? One is possibly things that look like second order effects, I think they're crucial. The second one, and we've seen this in specific cases, is you can start butchering your cost functions as long as they, keep a bit of the information, you still get the conversions. And this is, Irina's seen this, other people like Eugene Gidonowski have seen this, we've seen this, you've seen this. I think that's the point, is how are we going to butcher the way we propagate the information that is either biologically plausible or better for the kind of hardware / systems we have.
I know. I mean, ideally, if you could do completely parallel computation, would be wonderful in online. Right now, it's only partially parallel, right? The only parallelism is weight updates, and you still have to propagate the activation sequentially. So it's not, in that sense, it's not completely.
This might be butcherable.
Maybe, yeah. And as I said, there is so many design choices in this algorithm regarding the schedule of alternating minimizations, which could be crucial, which are not really explored. And, well, I forgot to say the most important thing. Just like with everything else, hyperparameter optimization was the key. Yeah, and of course, we spent as much time hyperparameter optimizing SGD, Adam, this thingy, just to give it fair chance. But still, it's quite a...
Let me put it in a different way. What's going on in going to have to converge to a fixed point.
Yes.
Convergence is computing the solution of the system.
Sure.
It's trying to find a minimum.
I agree completely.
And it takes time.
I agree completely. Now, but okay, so here's a second question, which I think is so my guess is going to be per the company, per my thought, non-orthogonal to the gradient. It is some guarantee.
Non-orthogonal to the gradient.
Right, of course.
It's
So
closer
then-
to a second order method.
That's
Yeah.
right. Yes, exactly. So in fact, this is still a way of doing gradient descent to some extent, arguably.
Yeah, it's just
Okay.
doing
We're all
it
on the
this.
same page.
Yeah.
Cool.
It just breaking the chain, pretty much,
Yes.
for various numerical reasons. What about the neuroscientific reasons? As I said, I am help. If it helps, helps. If it's not completely connects, well, what can you do? But the goal is we had experience with neurogenetic online dictionary learning, which was inspiration for similar algorithm and unsupervised setting where architecture would be expanding and compressing. And as inspiration, it was good. And for neuroscientists, it was a simple computational model showing why it's computationally kind of advantageous to have adult neurogenesis. When environment changes, then you have more of it, and you can show that. For AI folks, they said, okay, good paper, except just remove neurogenetic from the title, please. Well, we didn't. We left it. Anyway.
So now let me provide an argument against target.
Okay.
Is the fact that at the end of the day, we're going to make a very small change of the weights. We're going to make a small change, and because we're going to be doing online, right? We can't.
Yeah.
We're not going to be solving the weights for some.
Yeah. And depends on mini batch size, of course.
Yeah, but it's still
It's
you want to make very
Yeah.
tiny weights because for nonlinear problem, you're going to have millions of updates. Each of them is going to be very small. Okay, So what the implications of this? There's no point in looking at values of the activations that are very different from the ones you had in the feed format. Because anyways, the only thing you're going to be able to do is nudge them only a little bit by the weight change. So the conversations you're doing with target proper, you say, well, what if how the activity to be substantially different, not just waiting for something like this. Okay. The only case where my argument fails is when you have like discrete.
Yeah, like binary nets. Yeah.
That's right.
Yeah.
And then of course the
Yeah, you
small
just
change argument doesn't work because
Yeah.
you want a big change.
could be. So yeah, for binary nets, that's why folks at IBM were interested in that thing for neuromorphic and other like hardware. They're still interested. Yeah. So anyway, what I wanted to say also, I mean, all this optimization of weight stuff reminds me about the recent ICLEAR paper. I forgot exactly the title, but basically that weights do not matter. They can be random, right? Have proper architecture. What do you think about that one? We should discuss it in reading group. I'm curious.
So we
because
did that paper. Yeah.
Okay,
We did that.
but yeah, maybe we can take it offline. I'm just curious because what did it show?
Are you talking about David Haas' paper?
I think, anyways,
Weight agnostic.
weight agnostic. Yes, weight agnostic. So why it was?
There's a new one. Oh no, but that one, that's
learning on top.
yeah, that one they use gradient descent to discover the subnet.
Oh,
Sam,
You still learn.
they use
Okay.
gradient descent to discover the subnet. Definitely do. I can show you the paper. That is basically just a different training algorithm, which is yet again.
okay.
David Haas' paper is the one where they literally just take they initialize they optimize on the network architectures, find networks that can operate with random variables, and
So it's like stable to the weights, pretty much. It's like robust to like whatever, almost whatever you give it to it. Architecture is robust.
sort of, except that you see the funny thing is, so here's what they ended up doing is they have to optimize networks that work with a single weight value. And the reason they do that is because it takes too long for them to search through networks where the different synapses can have different
Arbitrary
weights.
values. Interesting.
And this gets back to the issue with any kind of evolutionary approach. It's great if you have forever.
Well,
million years. Not so great when you actually want to train.
interesting. Well, random weights is a whole separate topic because I was also curious about again a clear paper on the echo state nets, which supposedly work, not the liquid state, whatever. So basically reservoir computing.
But that doesn't work.
It was supposedly doing better than RNNs and LSTMs on.
Yes.
Okay, on which task?
Trivial.
Trivial. Okay, so it was some language task again. Yeah, although it kind of made me curious just to do a bit of a literature search.
Why not mention